the meeting is over and Melissa has an opportunity to do so later today or tomorrow. So with that, there are also, as most of you know, a chat function with Teams, and if you are chatting amongst yourselves, that will also be part of the recording that is posted, so just for your awareness. But if you do need some technical help or having a difficult time navigating Teams, please do use that function for Melissa or Andrea to help you out. So with that, Melissa, why don't you start recording?
Okay, the meeting has been recording or is recording. Thank you.
All right, well, thank you. Good morning, everybody. This is December 21st, 2020. This is the second meeting of the Vermont Climate Council. We have a majority present for this meeting, and I will call the meeting to order. And everyone should have the agenda. It was emailed to the council members, and it's also on the website, and within the body of the document, there are links to 2 of the 3 presentations we're going to have today. I will just highlight the meeting today is a continuation of laying the fundamentals for the council and those who are observing the council proceedings. And today we are going to have an overview of the climate change in Vermont from Dr. Leslie-Anne de Poignet-Giroux. I hope I didn't butcher that. Our Vermont state climatologist will have a review of Vermont's
and or transcribed.
Excuse me. We'll have secondly a greenhouse gas emissions profile from the Department of Environmental Conservation and an inventory of our existing programs that impact greenhouse gas emissions, which is something that the council is required to develop. And so DEC is going to, and the Department of Public Service will be presenting the inventory of existing programs to get you up to speed on that. So the first order of business today is to approve the minutes from the November 2020 meeting. The minutes are linked again in the agenda, and I'll entertain a motion to approve the minutes.
So moved.
Is there a second?
I'll second.
Is there any discussion about the minutes? And if council members have comments, please raise your hand and Melissa or Andrea will call on you.
No hands are raised.
Okay, so we'll try this by a voice vote. Council members only. All those in favor of approval of the minutes of November 2020, please say aye.
Aye.
Anyone opposed? Anyone abstaining? Okay, the minutes are approved. Thank you. So without further ado, we will move to the second climate change in Vermont item on the agenda. Dr. Leslie-Anne de Poignet-Giroux is the professor and state climatologist at UVM. She's a professor of geography. She specializes in climate hazards and severe weather with a special focus on flooding and droughts. As an applied climatologist, her research interests intersect a number of interdisciplinary fields, including hydroclimatic natural disasters and climate literacy, as well as the use of remote sensing and GIS in climate research. She is Vermont state climatologist, and as such, she engages directly with community groups, federal and state agencies, and national climate organizations. She facilitates and promotes dialogues among meteorology, climatology, emergency management, agriculture, forestry, and GIS interests. We're very fortunate to have her as a member of the council and as our state climatologist. And without further ado, I would like to turn the podium over her, so to speak, to present her piece on the climate change in Vermont impacts, risks, and adaptation. So thank you, Doctor.
Thank you, Secretary Young, and good morning, everyone. Okay. Is everybody seeing my screen okay?
Yes.
Yes.
All right, thank you. So, good morning, everyone, and it's again a very distinct privilege to be part of the Vermont Climate Council. And what I would like to do today are a couple of different things. First, I'd like to update the testimony that I had given to the House Committee on Energy and Technology on H688, which became the Global Warming Solutions Act that I gave back in January of this year. And then talk a little bit about some of my work on a national climate assessment that feeds into what climate change looks like in Vermont, and then end with some additional resources that are going to be available to us. This is a high-level overview. It's a sort of 30,000-foot presentation of climate and climate change across the state. And I view this as a sort of ongoing sort of report out briefing type of thing where after we've done this sort of verbal piece, I'm going to take some time and actually put some things into a written document so that we can have that to refer to as we break up into our subcommittee work and step forward in all of the things that we are going to be accomplishing over the course of the next year or so. So just to sort of set the context here, this is a visualization that shows us warming trends, warming patterns across the entire world. We're going to do a sort of funnel shape from a global perspective all the way down to a local perspective here in the state of Vermont. And what you're going to be looking at was generated by NASA, and it takes us through 5-year steps of what the temperature across the entire world has looked like relative to an average period. And we're going to see how that warming and patterns have changed over time. So I'm just going to play this through. I know some of you may have already seen this because I always start off a lot of my presentations with it. So we're starting in 1880, and we're stepping through 5-year time slices. We're in the 1915s now, heading through the world wars coming up, heading through to the 1950s, the 60s, which were particularly cold, and then we get into the 70s, 80s, when that anthropogenic, that human signal became particularly strong. And you're seeing that very marked warming signal, warming trend across the northern hemisphere particularly. And so when we're thinking about climate, we're looking at all of the pieces of our earth, our land, our vegetation, our water bodies, and how they all sort of fit together in terms of energy, in terms of moisture, in terms of where it rains, where it snows, all of the moisture that makes its way down through to the rivers and lakes and streams and ponds, what that does in terms of vegetation and so forth. And so any change in any one of these pieces of the climate as a system is what we are looking at when we're looking at climate change. So we're looking at changes in the amount of energy in the system. We're looking at changes in terms of where and how much rain falls, where the clouds are the clouds changing, looking at things like sea level rise, lake level rise, changes in your soil moisture, whether we have droughts or floods, but also from an atmospheric chemistry perspective. And so looking at different amounts of aerosols in the atmosphere, changes in our chemistry. What does that mean for our ecosystems, ecosystem services? And the warming that I showed you on the previous couple slides, that warming piece is one element of looking at climate change's entire system. So we're going to try to make sure that we have all of those components in place as we sort of step on through. So when we think about climate change, we can think about it from either the process as to why our climate is changing. So whether it's from changes in your greenhouse gases, burning of fossil fuels, changes in land use patterns, so deforestation in the Amazon, for example, And what does that mean in terms of the impacts that we actually see? So sea level rise, when we have bird migrations changing, when we have phenology changing, sugar maples budding earlier, for example, those are some of the impacts that we can look at. And then what are some of the strategies that we can employ to try and either mitigate against climate change or to adapt to climate change? So we can break it down into processes, which are these oranges and yellows on the left-hand side here. The middle section here are the impacts of climate change, and then the green on the right are the different strategies that we're going to be looking at. And so our work here as a council fits primarily into this last section here, this section on the right, which is looking at what are some of the things that we can do from primarily a mitigative perspective in addressing climate change. So let's pivot a little bit, and let me tell you a little bit about some of the work that I did as part of the 4th National Climate Assessment, which is abbreviated as NCA4. So the 4th National Climate Assessment was published in December of 2018. And it was broken up into 2 parts. One part talked about all of the physical science that we know about, and then the other part talked about the impacts, the risks, and the adaptation in the US, the contiguous US, Hawaii, and the associated Pacific Islands, Caribbean, and all parts of the country as a whole. So this National Climate Assessment came out of the congressionally mandated US Global Change Research Act of 1990. And the language in the congressional mandate specifically says that as it's written, it's designed to be relevant to policies, be it regional policies, state policies, all the way up to national policies, but it cannot be policy prescriptive. So what you'll see when you read through the National Climate Assessment is that you don't see words like you must do this or you should do that, because that would be policy prescriptive. What it does instead is to look backwards over time and look to see what are some of the developments, the pieces of progress that have occurred since the last climate assessment, and then put those into one place, into context, for us to understand what climate change looks like here in the present and now. And so this last climate assessment that we saw in 2018 saw a really, really big push to make sure that the regional pieces of information, the regional work that we do here in the Northeast and across the entire US was actually kind of bubbling up and being understood within the context of what climate change looks like. So there were a lot of case studies, a lot of specific examples, a lot of things that we were learning about, like Hurricane Irene, Hurricane Sandy, and how those affect us in various parts of our socioeconomic sectors. So part of that, here are the regions across the National Climate Assessment. Part of that was there was some pre-work that was done in support of the National Climate Assessment. And one of them is something called State Climate Summaries, which is what you see on the right-hand side. And if we have some time towards the end, I'll pop out to the website and show you what that looks like. Each state has a state climate summary. And if you just search for it, search state climate summaries, you will come across this website that shows you by state what climate change looks like in that particular jurisdictional boundary, including things like flooding patterns, including things like what the warming looks like, what the lake levels look like, and so on. And so those are some of the pieces that were put into place in support of the 4th National Climate Assessment. Now, as we were putting that together, we were challenged to think about what are the pieces of our region, so the Northeast, which includes Vermont, New Hampshire, Maine, all the way down to DC and West Virginia, upstate New York. What are the pieces of our region that are unique, that differ from, let's say, the Southeast or the Caribbean or the Pacific Northwest? And a lot of that has to do with the fact that most of our region, most of the Northeast, is actually rural. And so the patterns and the changes that occur as a result of our changing climate look different across, whether we're talking about the inland parts of our region, which is where most of our rural landscape is found, found versus what's taking place on your coastal parts of the Northeast, which is where most of the largest cities are found. And the other pieces that are challenging for us is that the Northeast is one of the oldest settled places in the entire US. And so the length of our settlement has a lot to do with the culture of the region, the cultural heritage, has a lot to do with our infrastructure, and all of that is overlain on top of the physical geography of our region. The fact that we have a lot of mountains and valleys and how those play out in terms of either storm systems, in terms of how we observe climate change. So part of the piece that was new for the first time is that we actually had economic information to sort of calibrate against. And this included things like changes in number of lost days as temperatures are increasing, changes in terms of air quality conditions. And both of these are coming sharper into focus, sharper into point as we think about 2020 and sort of set it against how our year has sort of evolved in time. And as you're looking at this diagram here, a couple things that you probably have noticed or have seen in other places is this reference to two scenarios or two sort of bounding boxes that we're looking at these changes as we look at them being projected out into the future. And you will see this acronym RCP, which stands for Representative Concentration Pathway, the upper bound that we used in the National Climate Assessment of 8.5, and then the lower bound of 4.5. So let me take a little sidebar and talk about these for just half a minute or so, again, to sort of place it into perspective. So these representative concentration pathways, or RCPs, are the new way of talking about scenarios that factor in greenhouse gas emissions, land use changes, policy changes, and how that warming signal is projected to sort of play on out relative to emissions into the atmosphere, relative to what we do as human beings on landscape, relative to changes in policies that might come down the line. And so on the left-hand side here, you see the representative concentration pathways from a carbon emission perspective. So here's that 8.5, which is sometimes referred to as business as usual. And then the lower bound that was used in the NCA 4, which is 4.5, and that's taking some fairly aggressive policies to actually cut your emissions so that we start trying to change the trajectory of where we are from a scenario point of view. So that's on the left-hand side. On the right-hand side, you're seeing the response in terms of your temperatures. And so you're probably saying, but if the policies were so aggressive, why are the temperatures still going up, which is what you see across in here. So 8.5 is your red, 4.5 is your blue. And then even with all those really aggressive changes from a policy perspective, the temperature still goes up because there's something called inertia in the system. So even if we stopped all emissions today, all of the sort of the gases that are already in the atmosphere would continue to warm the atmosphere for a certain amount of time. And so that's why you see these values still sort of going up, even with those fairly aggressive policies. So what are some of these gases that we're talking about? So this is a diagram that comes from the International Intergovernmental Panel on Climate Change, IPCC. And what it shows us is the gases that are greenhouse gases, other gases that are critically important to us, and then factors like aerosols and clouds, organic carbon, and so forth. And as you look at this diagram, what you're looking at is there's a zero line in here, and anything to the right of that zero line means that that gas is warming the atmosphere. Anything to the left of the line means that that gas or that component is actually cooling the atmosphere. So the one that we know a lot about is something like carbon dioxide or nitrous oxide, and we can see that the warming signal very, very strong in here. What we can also look at are some of these other gases like methane. And methane, even though it has a smaller value relative to carbon dioxide, methane is actually has the potential to warm the atmosphere 20 times more than carbon dioxide does. And so when we're looking at our emissions and reduction of our emissions, we should really try to make sure that we're looking at all of the gases that are having an influence on the atmosphere itself. And so some of the other things that are important to us are, of course, aerosols. And if you're wondering why aerosols can be both warming and cooling the atmosphere at the same time, a lot of that has to do with the type of aerosol, the size of it, and where it got pumped into the atmosphere. So aerosols and warming and cooling of the atmosphere became a particularly important piece during this year as we looked at forest fires, as we looked at fires in Siberia, as we looked at a lot of the aerosols that were being pumped into the atmosphere set against the backdrop of COVID-19. So speaking of that, one of the gases that is important to us, nitrogen dioxide, is a gas that we saw these very, very sharp and marked decreases in March of this year when we went into pretty much a global shutdown. And so a lot of the industrial activity actually ceased. And we saw these dramatic drops in nitrogen dioxide, which, as we know, is also a greenhouse gas. And so the thought was, is this an experiment sort of playing out in time as to what would happen if we decreased the gas due to activities that were very, very dramatic. And so nitrogen dioxide is an interesting gas because it depends very, very heavily on our weather conditions. And so part of the reason why we saw that very, very rapid shift when we went into shutdown is because it depends a lot on those day-to-day conditions in your weather. And so those drops in nitrogen dioxide, we saw them in northern Italy, we saw them in parts of China, but we also saw them here in the Northeast. And so on the upper part of this diagram, we have a 5-year average time frame, and the darker the color, the more intense the concentration of nitrogen dioxide that we're looking at in the atmosphere. And so you see the megalopolis along from Boston all the way down through to New York, down into Jersey, all the way down to parts of DC and so on. And then with that shutdown period, these dramatic decreases in nitrogen dioxide were observed. And so this is March. If we stopped in March, we would not have gotten the full picture, because as we reopened our economies and went back to business, again, because of the process and the dynamics and the way that nitrogen dioxide plays out, it actually rebounded in the post-lockdown period. And so here we have that rebounding of those values as a result of increases in our industrial activity again. And so let's pivot back to NCA4. Let me tell you a little bit about the Northeast, and then we'll get into climate change across Vermont and what that sort of looks like. So if I brought it all together, and I know you cannot read this diagram because of all of the fine print in here, what this is designed to highlight for us are the very different impacts in climate change across all of the US, and the actions that are being taken to sort of mitigate or to adapt to climate change. And so in the Northeast, it says the impacts are in water, energy, transportation, infrastructure, as a result of things like snowstorms, droughts, heat waves, and flooding. And some of the actions are looking at making investments to increase the resilience of our infrastructure. So I actually had to do a presentation like this in January of 2019. And so I went back through and I read all of the regional chapters to see were there any common themes. And so some of the common themes that sort of popped out were the importance of looking at human health, the importance of looking at our indigenous peoples, looking at the adaptive capacity of our landscapes, whether we have changes in agricultural productivity, looking at the resilience of our infrastructure and transportation, looking at coastal services, ecosystem services, and for the parts of the US that have a coast, sea level rise and how that sort of plays out for us. So pivoting to the Northeast in particular, there were 5 main points that were made in the Northeast chapter. And the first one focuses on the rural parts of our landscape. And we'll talk about the dichotomy or the juxtaposition with the urban parts of our landscape in a sec. But for our rural parts of the landscape across the Northeast, we're looking at how our seasons are changing. We're looking at changes in when springtime is coming a little bit earlier, changes in the fact that we don't have as distinct seasons as we used to have, and what are the impacts that all of those changes have on things like tourism, in terms of forestry, and all of the industries and livelihoods that depend on having very clear seasons, having seasons with certain temperatures, getting certain amounts of precipitation in those various seasons. And so as we look at this again, remember we're doing this rural piece because over 80% of the region is actually rural. And so one way of looking at those changes in our seasons is to look at growing degree days, or to look at the length of our growing season. So on the left-hand side is the last spring freeze, and on the right-hand side is the first fall freeze. So in between that gives us an idea of the length of the growing season. And the way the color scheme is set up is the yellows mean that those dates are getting longer by anywhere from 6 to 14 days. And the more reds tell you that there are changes anywhere on the order of 22 days as much as 30 days. So we're looking at 2 different times. So what we call the middle part of the century, so 2040 to 2069. We're looking at the relatively aggressive scenario, so RCP 4.5 in this one here, and that change is somewhere less than about 18 degrees between these 2 times. But if we do business as usual, the RCP 8.5, we're seeing that those changes are much larger. So over 18 days difference in our length of our growing season. And then if we go even further out in time, this is called end of the century, so 2070 to 2099. And again, that's still at business as usual. We're looking at very, very large changes in our growing degree and those growing season timeframes in here on the order of anywhere like 26 days or more. So another way of looking at this really quickly is to look at the timing of our snow-related stream flow pattern. So we're looking at when is that occurring. So it's occurring earlier and earlier. And the red triangles mean that timing is occurring at least 10 days earlier compared to the longer term average, and your oranges are anywhere between 5 days and 10 days earlier. So you see across our state, earlier spring stream flow taking place in that 5 to 10 days earlier relative to the average period. And the authors who did that work, Glenn Hodgkins and Rob Dudley at the U.S. Geological Survey, they took a slightly deeper dive into that and looking at the changes in rainfall, precipitation over this average time frame here. And so again, increases in rainfall across pretty much everywhere. So for us, that's somewhere between 20 and 50% increase in rainfall across the state. Even larger values across places like Rhode Island and the eastern part of Massachusetts. And then related to that are these very large increases in our storm flow. So pretty much everybody has at least a 50% increase in storm flow across the entire region. So the second key message from the Northeast was looking at changes in your coastal patterns. And so when we look at our coast, some of the things that are important here are the fact that the ocean off the coast of the Northeast is actually warming the fastest out of all of the ocean regions in the US. And so that has a particular set of implications for us, especially when you combine it with the fact that sea level is also rising particularly fast in the Northeast. And how does that threaten our ecosystem services? How does that threaten livelihoods of our coastal communities? And so when we look at the ways in which that sea level rise and sort of inland flooding can impact our regions. We've got a little schematic here that was created by one of our NCA authors to actually show what this might look like for folks, let's say, who live in New York City, and why that might be important to know about sea level rise in addition to inland flooding. So speaking of New York City, let's talk a little bit about some of those urban areas. And here, the pivot point was the fact that our urban regions and our rural regions are highly interconnected. And the urban regions have their specific challenges in terms of infrastructure. Some of our oldest infrastructure is found here in the Northeast, and that sets up a different type of risk for us here when we depend on different elements of our infrastructure than it would for folks who live in the West or the Southwest or the Pacific Northwest, for example. We also have a very large number of historical sites, and we know that this is a critically important piece. We saw that in the aftermath of Tropical Storm Irene, when we started those really hard conversations about our historic downtowns and some of the things that we need to think about when we try to make our historic downtowns even more resilient. And so flooding is a large component in urban areas. It's also a large component in our rural areas as well, but it sets up a different dynamic when you're talking about flooding of large metropolitan areas. And so as a response to that, as an adaptation to that, when New York City got flooded as a result of Sandy, and then they thought about how to rebuild, this is one of those adaptation measures that was actually put in place. And so because the subways were flooded, when they went to redesign or to retrograde a lot of the sidewalks, what they actually did was to install these multi-use, multi-purpose grills that are about 6 inches above the actual pavement itself, so that the water doesn't go straight into the subway. And then, of course, you have the benches as well as the bike slots in here. So you've got a very nice example of adaptation. So the fourth key message was different in that it focused on our human health. And when we're looking at human health, we're looking at what are those challenges that affect us. And this is where it becomes important to look at where you are in the region, because human health impacts on the coast or in a large city are very different than they are in a rural part of our landscape. And so we need to factor in things like not just heat, not just water, not just air quality, sea level rise, but also things like Lyme disease and vector-borne diseases. We need to factor in all of the things that make us vulnerable, whether it is our age, location, languages, all of those things that make us vulnerable both as a community, but also as individuals as we think about how to increase our resiliency. And so back then, we were able to use emergency room visits to look at the ways in which heat was impacting our human health. Moving forward, looking at additional pieces. I always get asked about, what about Lyme disease? How are we factoring that in? And that's one of those gaps that we need to think about filling as we step forward in looking at human health. So the last key message in the Northeast chapter was talking about all of those great pieces of adaptation that were underway, that continue to be underway, and how do we make sure that they're being sort of collected in one place so that we can do lessons learned from one part of the region to the next. And so all of this would not have been done without the authors on the team itself. So here are all of my co-authors on the team. We had a number of technical contributors who brought their expertise or mapping or other case studies to the place. And then if you want a copy of the chapter, just head to NCA 2018.globalchange.gov to download a copy of the chapter itself. All right. So we've done this sort of global piece. We've done in Northeast. Let's continue down that funnel to talk about climate change across our state. And one way that we can look at how this sort of plays out is by looking at Lake Champlain, which by virtue of its size, by virtue of its depth, is one element in looking at not just what's taking place on the Vermont side, which is here. There's Lake Champlain, frozen in 2014, but what also is taking place upstream from us, so the Adirondack region, because all of that helps us to understand how this is playing out. And so from National Weather Service, we have some ice in dates for the main part of the lake, just in Burlington here, where it's widest. It's 12 miles wide at that particular point here. And so we're seeing that there are places or times when it did not freeze, and that's what these dots are allowed in here. And so one way of looking at Lake Champlain data is to look to see that did not freeze is becoming more and more frequent across in time here. Another way to look at what climate change looks like across the state is to look at springtime conditions. And so what we see, and we've seen this in history, but we're seeing this particularly more nowadays as well, is what we call a backward spring. And so instead of temperatures increasing and continuing to increase, what we notice in a backward spring is that temperatures start to increase, and then we go back into cold temperatures, and we even see things like snow. So this shot is the VTrans building in Berlin in May of a couple of years ago. Here are some blooms on the UVM campus from about 10 years ago. And so we're seeing a lot more of these. And if we were in a room, I would probably see you sort of shaking your head, because this sort of brings back some things that you've noticed over the last few years or so. And so we're thinking about how these changes continue to sort of evolve for us. In terms of temperatures, one way to talk about climate change is to look at how cold does it get at night. And so we're seeing that those nighttime temperatures are actually getting warmer. And we look at winter, spring, summer, and fall, and looking to see that these values are getting warmer, not just over the entire state, but over the individual seasons as well. Another way to look at it is the amount of precipitation, which is both snow and rainfall, and when those are changing over time. So again, we've got winter, spring, summer, and fall, and looking at all of these changes. And one thing that I want to point out is that these data come from, again, the climate summaries. So we're able to go back to 1895 and get the full picture of how these changes have occurred, so that you can see what not just the last 40 years, but also the entire 120 plus years of information looks like. So why do we look at all of these changes in temperature, in precipitation? Well, it's because as those temperatures are warming, what it means is that we're shifting to more record high temperatures, less record cold temperatures, but we're also shifting the average values. And so that means a different set of processes, different set of understanding in terms of temperature. And when we look at precipitation, what we're seeing is that we're getting fewer and fewer of those storms that bring us like drizzle type of rain, but we're getting more storms that bring us heavier precipitation. So again, that is important for us, because there are certain sectors of our socioeconomy that are critically important to those changes in precipitation, changes in moisture, changes in soil conditions, and so forth. And so just to run through them really, really quickly here: infrastructure, emergency management, human health, forestry, agriculture, tourism, and recreation. And we're looking at these across the board. Human health is one that is critically important. And as we look at it, we can look at temperatures, so high temperatures, and across the North Country here, we don't usually see a lot of 90-degree temperatures. And so some work by the Department of Health in conjunction with Dr. Evan Oswald, who was a postdoc with me a few years ago, we were able to identify this cutoff as 87 degrees when we start seeing particular challenges for us as human beings. And we also, again, need to factor in ground level ozone, because that has implications for us from a respiratory perspective, but also from a sort of vegetation perspective. And then as our changes continue, that has implications for Lyme disease and whether it becomes more frequent, more severe, and so on. So Scott Whittier provided this diagram here that kind of shows us where some of those very high temperatures tend to occur. So in the banana belt of the Champlain Valley, but also primarily in the southeastern part of the state, which is one of the warmer parts of the state. We don't tend to see that much in the higher, colder Northeast Kingdom regions as they play out. So vegetation, looking at changes over time, and one way to do that is to compare our plant hardiness map. So this is the older map across in here. Put a little box to show you where Vermont is. And then as our conditions have changed, we're seeing that sort of northward shift in our plant hardiness zones. And if you garden or if you use this for making your agricultural decisions, you would have noticed that these changes have actually started to occur. Josh Hallman at Forest Parks and Rec provided this diagram here that shows the changes in the growing season that we talked about 15 minutes ago. And this is from the work at the Underhill site and looking at those increases over time. So starting in 1990 to about 2015 or so, looking at those changes in our growing season. And at the same time, the sugar maple bud break at that particular site is actually getting earlier in time. So these are the dates of the year. And so smaller values mean that you're earlier in the year. And so we're getting that earlier bud break. And what does that mean for our sugar maples? Like I said, ground level ozone is important for us from a human perspective, but it's also important for us from a plant perspective, because this has implications for the sort of vigor with which this grows. And so Dr. Heidi Hales, this was one of her colleagues for a very long time, Rich Poirot, and this is some of the work that he had done in this space. And as we think about our changes in precipitation, changes in moisture, what does that mean for recreation? What does that mean for tourism? Snowfall conditions, drought conditions, leaf peeping conditions, especially when we have droughts. What does that mean in terms of the brilliant fall foliage that we are known for as a state? And then in terms of infrastructure, looking at our roads and highways, looking at our electrical grid, for example. What about our water supplies, be they municipal or other supplies? And then critical infrastructure, which is where emergency management is particularly interested as well, in how do we make sure that our critical infrastructure is being protected. And so all of those pieces from an infrastructure perspective are important, because as we see more and more of these extreme conditions, extreme events, floods, droughts, forest fires, all of these are going to have particular challenges for our infrastructure in terms of, especially this last piece here, which could look like some of the things that we saw in the aftermath of Hurricane Irene, because a lot of our roads and rivers are very, very close together. And so this is the town of Waterbury. And during Irene, we saw that sort of pinching off in this part of the landscape in here. So looking at that and looking at these places where we know we're going to have these challenges from an infrastructure perspective. So Jonathan Croft, VTrans, put together this map that shows you the Irene damage, which are these colored highlights here. So the greens, the reds, and the yellows show you the places that were particularly damaged in Irene. And what he did is he overlaid that on a flood map from 1927. And if I do a blow up here, you'll notice that a lot of those actually kind of match like this, because of the way that the again, physical geography kind of plays out in terms of setting up certain vulnerabilities across the state from an infrastructure perspective. And so if we look at strategies, which is what most of what we're going to be doing as part of this council. So again, just to remind us that we're on the right-hand side here and looking at mitigation and adaptation. One of the things that we found in National Climate Assessment was that there's still a lot of work left to be done in terms of reducing risks and as we play out that sort of greenhouse gas emissions, which is what we're going to be working on for setting up our plan. What are some of the things that we need to sort of also keep in mind, and the sort of co-benefits that could occur as we reduce greenhouse gases and their emission into the atmosphere? What are some of the co-benefits in terms of improving air quality, restoring our ecosystem health, making our infrastructure a little bit more resilient? And so if you make a note of chapter 29 in National Climate Assessment, it talks about all of those pieces that we already have in place in terms of mitigation. And so these dots on here show you all of the mitigation types of activities that have occurred between 2014 and 2018. And if I blow this up just a little bit more, not sure how well you can see this, focusing on a per state basis here, and not just the number of these mitigation activities, but the type of them. And so from Vermont, most of our mitigation activities are in transportation, but we also have mitigation activities in our greenhouse gas target and the caps and the pricing around that. Also some work that we have done in energy efficiencies, forest and land use, and then renewables, okay? So all of these color-coded along in here, you can see what they sort of play out by state as we look at that. And so infrastructure is a big piece for us. It was that largest sector on the previous chart on here. And as we're looking at that and we're thinking about how do we, again, increase the resiliency of our infrastructure, but also how do we sort of meld this with looking at our greenhouse gas emissions, thinking about some of the maybe changes in design, changes in planning, in ways that allow us to do a win-win-win as we look at changes in reducing our greenhouse gas emissions. And so the corollary to that is adaptation. And adaptation is found in chapter 28. And as we look at the ways in which we're making progress in terms of adaptation, this is one of my favorite diagrams, because in 2014, we were just starting to get on making progress with looking at this. And by 2018, we had so many more success stories to look at. We could include things like Reggie in there. And so how do we continue to make this so that the next assessment, we can make this sort of full circle and start to evaluate how well we have done in all of these practices? And so looking at ways of doing mitigation at the same time as adaptation in a way that helps us to maybe look at the work that we're doing through the lens of 2020, through the lens of equity, through the lens of social justice, through the lens of human health, and all of these pieces that are sort of now with us as we become more and more aware of the co-benefits that could occur. And so as we look at human health, I've mentioned that a number of times because it comes back to us in terms of who we are and making sure all of our communities, our vulnerable communities, are being served, and making sure all peoples are being included as we look at climate change, as we look at the ways in which all knowledges, all ways of knowing are part of our conversation in terms of ways of mitigating and adapting to climate change. So I just wanted to end with some additional resources that I have not had a chance to touch on, but hopefully maybe in another briefing, or as we continue to look at some of these pieces of the puzzle, we will get a chance to take a look at. And Dr. Jason Schaefer, Dr. Jay Schaefer at what was Lyndon State, now Northern Vermont College has done some work on climate change, particularly from an electric grid perspective. And so I just pulled out one of the pieces of a PowerPoint that he sent me right after our first meeting, and looking at the ways in which you can sort of slice and dice these changes in heavy precipitation from a county level perspective and also from a temporal perspective. So we're seeing a lot of the changes in heavy precipitation where they are. So this is the spatial component, but also when. And so a lot of this is a sort of fall time frame that's pushing those average annual values that you're looking at. Something else that's coming online is the second Vermont climate assessment, and this is now getting off the ground. And so Dr. Jillian Galfa, Dr. Josh Faulkner, and myself, and Dr. Leanne Holterman are the sort of team that's leading this. And so we're getting the data pieces in place, and some of the sort of revisiting some of the different chapters that were written were published back in 2014. And then the last piece is the state climate summaries that I mentioned before. And then finally, Maine has actually done a climate council. They started, I think, a couple years ago, and so this is their report. So it's December 2020, so it's literally hot off the press, and it's maybe something that we can look to and see what they've done, maybe some lessons learned, and ways of thinking about how do we craft some of the work that we're going to be doing in our subcommittees. So thinking about all of this and looking at the ways in which climate change, weather, short-term, long-term, how we are going to sort of look at all of this. Different scales are going to be critically important to us, trying to make sure that we are doing this from a system science perspective so that we don't miss piece of the puzzle, looking at our populations, all of our populations, making sure that we are being sensitive to our geographies of vulnerability so that as we craft all of these different policies, we are making sure that all of our populations are being served. And then, as we step on through, we're going to be doing some really, really hard work for the next year or so. Some information is probably going to come online, and that might sort of have us in a place where we need to be a little bit flexible and nimble as we respond to the new information that it comes online, so that we produce the best report as we sort of step through. So I thank you for our time, and I believe I have a couple minutes. So what I'm going to do is I'm just going to pop out of here for a sec and head into a couple places that I wanted to show you. So this is the state summary for Vermont. And again, it's set up very, very similar to both the National Climate Assessment as well as the Vermont Climate Assessment in terms of having key messages. All of this stuff is available for download. And so all of the stuff that you are maybe interested in, so number of hot days, cold nights, for example, temperatures in different seasons, blowing that up a little bit, precipitation over the entire time frame that we can look at. What does this mean for those extreme events that are important to us? Changes in precipitation in one particular time of the year. And then this work is going to be updated hopefully by the end of next year, so we can actually have this online. And then the last thing is a quick look at, here's the Maine Climate Council. And as we step through, I believe it's 200 and maybe 17 pages long. And so just to give you a quick sense of the work that was done as part of their council. And again, the various things, meetings, the members, very similar to us, the impacts and so forth. So with that, I'm going to stop sharing my screen. And I'm going to turn it back over to Secretary Young.
Thank you very much. That was a really great overview. And I think we would like to at least get your PowerPoint linked with the minutes so folks can spend some more time with the slides and get a better understanding for those of us who are not as high on the learning curve as many of you. So would that be possible to do that?
Mm-hmm.
Yeah, Melissa will
Sure.
work with you.
Okay.
We have just a couple of minutes, but certainly if folks on the council have any questions, I'm sure the doctor will be happy to take them. So Chris Campany, your hand is raised.
I was just wondering, with the change, I know we're expecting more precipitation, but in, I guess, more frequent. Well, as you noted, we're going to be losing the, as we've kind of seen, we're going to be losing the drizzles, and more rain is going to be coming at one time. But I think I also saw that we should be expecting more summer droughtiness like we've been experiencing. I'm wondering if there is any anticipation that we should be taking into account greater wildland fire risk, because I know when I moved here about 11 years ago, I was told about Vermont's remarkable asbestos forests that don't burn, and land use planning in Vermont. We don't talk about wildland fire like we do in other parts of the country, and I'm wondering if we should be changing our assumptions around that for the resilience piece of this.
That's a great question, Chris. And the way that you framed it is that whole system science piece, because fires are part of our landscape. They may not be as prevalent now as they were in the past. And if we're going to look at changes in moisture patterns, looking
I don't know if it's me, but I believe Leslie Ann may have frozen.
Yeah, it's not just you.
Okay. Leslie, if you can hear us, we can't hear you. Okay, Melissa, perhaps you could send her an email or send her a note, and then we apologies for her freezing up, and we can get back to questions as soon as we get her back, I believe. So I know, Abby, you have your hand up, and Chris, your answer's only half half answered. Your question's only half answered. So perhaps we should move on now to the 9:30 presentation, and we can loop back to Leslie Ann as at the end of that.
Madam Chair, my question isn't a question. May I just offer a quick?
Sure.
So I reached out to my friend Rich Holshoe, who is a member of the Abenaki tribe, and I wondered if I could just offer a land acknowledgement today as we move forward in our work. The land we call Vermont is a part of the unceded homelands of the Abenaki people, the Mohican people, and their kin from time immemorial. The ongoing policies and processes of colonization that actively disparaged and displaced Indigenous peoples have also contributed in great part to the challenges of global climate change with which we are now faced. The Abenaki continue to live here in relationship with the land, and the cultural values that have sustained them in place for millennia are worthy of examination and emulation. As we treat each other, so we treat the earth. And it seemed an unfortunate oversight that there was not an Abenaki representative appointed to the council, and I thought that at the very least we could offer an acknowledgement of the unceded territory on which we all sit, work, live, love. Thank you so much, and Dr. Depini-Giroux, that was a wonderful presentation. Thank you.
Thank you, Abby. Melissa, do we have Leslie Ann back?
If I say something, can you hear me?
Oh,
Yes, we can. Thank you.
And I dropped out at the worst possible time because I missed almost everything that Abby said. Absolute worst possible time.
I
Oh
can
my
type
goodness
it
me.
into the chat if that helps.
Or
That
send
would be
it
great.
to me as an email, please. Please.
Okay, sure.
Yes. Yeah. Oh my
And
goodness.
it will also be on the recording that's posted. So
Mhm.
I think you were in the middle of an answer to Chris's question.
I was, and it's like, oh my goodness. Well, at least I made it through the actual presentation without disappearing. Okay, so yes, I was saying that absolutely wildfires need to be factored in from a soil moisture perspective, but also from a dryness of the air perspective. Are you still hearing me? A bit okay. Okay. Part of the reason why we look at climate change over a long-term perspective is somebody said to me once that we've never seen droughts as we've seen here before. And so I went back and I looked at how dry it could be. And back in the 1700s, Vermont was so dry that wetlands started to burn and burn for years at a time. And so when we think about forest fires, yes, absolutely, they need to be part of the equation because otherwise we're going to be missing part of that landscape piece. So yes, Chris, absolutely.
Well, thank you. So the next item on the agenda, see no other hands raised, is the Vermont's current greenhouse gas emissions profile. And we have the Commissioner of the Vermont Department of Environmental Conservation, Peter Walk, and Colin Smith from an environmental analyst for the Air Quality and Climate Division in that department. So Peter and Colin, you're up.
Secretary Young, I believe you have another hand raised if you want to go to Rich before I start.
Sure. Richard? Richard, can you hear us? Richard, your hand is raised. Well, clearly we're having some auditory issues with Richard as well, and we'll continue to try to bring him in for his question. Thank you.
He did something in the chat.
Oh.
He said many people assert that climate change is not real. The recent observed changes are not just temporary blips. What parts of the assessment most support the view that these changes are linked to global climate change rather than just temporary?
Thank you very much, Angela.
Yep.
All right.
Did you want me to answer that, Secretary Young?
Sure.
Okay, so I think the best way to answer that is to look at it in a long-term perspective. And when you look at least 200 years of information, it allows you to see the changes that we're seeing now, especially the acceleration from 1980. And that's the sort of anthropogenic, that's the human related piece. And when you set that into the context of the longer term and you see that those changes have been occurring for 200 years, then that allows you to understand that it's not a temporary thing, it's part of a longer term piece. And the human piece in terms of that acceleration, where that sort of fits in. And so you're not sort of pulling just 40 years of information, you're looking at it over the longer time frame and seeing that the changes continue to occur.
Thank you. I think we'll have time for one last question, and we'll move to Peter and Colin so that they have time for their presentation, and then if we can come back around before the break for additional questions, we'll do so. So Adam, you have had your hand up next. Adam Newts.
Yeah, thanks. Good morning. I'm an energy professional for 25 plus years. Myself climate knowledgeable, potentially even fluent, and the information presented in your PowerPoint presentation, a vast majority of that, and a multitude of different types of evidential proof of impact is it's overwhelming. And so I think one of the comments, or one of the things that I think this council needs to continue to do is think very clearly about what our message is to the overall population in what we're doing and what this data is telling us, right? There, to I think Rich's comment, there's still some people that believe that this is not connected and it's potentially temporary. And, you know, that was just an extremely powerful, succinct presentation from multiple different angles that I don't think most people know. And I think we should just at least note that we've got to get some of your work, Doctor, and that of your colleagues out even more succinctly and more cleanly to the Vermont population and beyond. Very important and disturbing.
Thank you for that comment, and thank you for the challenge to make it more widely accessible. I think we don't do enough of that, and I thank you for that challenge.
All right, Suzanne, if you'd like me to get started, I'm happy to. I'm going to share my screen.
Please do.
And it should be up now. If you can let me know when you can see that. I'm doing it in PDF form because it's a little bit easier and doesn't take over my whole multi-screen world. So if somebody could confirm that they can see that.
I can see it, Peter.
Okay, great. So good morning, everybody. For reference, I'm Peter Walk. I'm the Commissioner of the Department of Environmental Conservation. Looking forward to working with all of you to advance this important effort. I appreciate the presentation greatly that Dr. Tupinian-Giroux just gave us. That really is your climate change 101, 201, up to 401 briefing in terms of really setting the stage for where we are and where we need to work towards as a state. Before we get into the greenhouse gas inventory itself, I want to talk a little bit about a few sort of 101 style definitions to make sure that we're all on the same page as we work through this. But you're going to hear over the course of this presentation the one to follow, and then presentations in January about sort of the status of work that the state and its partners are doing to work to address greenhouse mitigation, resilience, and adaptation measures. But I think it's important to sort of set the frame in the larger context so that we're all speaking the same language, and also to give you some framing around the emissions profile itself, what we often call the greenhouse gas inventory, and what it is and what it isn't, and what it and how it ties into the goals that have been set for us in Act 153. All right, so I just some of these will seem fairly basic to some, and at the same time, I think it's really important that we're all speaking the same language. We talk about mitigation, adaptation, and resilience, and we use them all in some ways interchangeably, but they're not interchangeable, and we need to make sure that we're being clear on what the distinction is. The mitigation side of the house is the work that we do to reduce the impact that greenhouse gases are having on our climate. So that either becomes through the reduction in emissions from sources of emissions, which we'll go into later, or it involves the active work to store those greenhouse gases. So we'll talk more about sequestration and natural and working land activities on January 4th, but that's that piece of the house. The climate adaptation and climate resilience piece are often used interchangeably, but I just want to sort of describe the reason why those things are different. Adaptation can be both a passive and an active process. A passive adaptation would be the way in which the world is going to change, whether we do anything or not. We live on a giant rock that will still be here and will adapt and evolve to whatever climate exists on it. The ways in which we adapt and we change the way our systems function is more of that human-driven adaptation. And that human-driven adaptation speaks to the resilience of our human system. What are our individuals, communities, and natural and built systems able to withstand future climatic events, trends, and overall disruptions? Quickly going into what constitutes a greenhouse gas, we talk primarily about carbon dioxide. I appreciate that Dr. DePinay talked about other gases as well, and we'll talk a little bit about more of those in a moment, because while carbon dioxide represents the largest in terms of number of molecules out there, it is in fact kind of the baseline for what we think of as potential for warming activities. We'll talk about two types of greenhouse gas emissions, those that are human-driven, the anthropogenic ones, and where the focus of our inventory is, and the goals that have been set for this council, or the requirements that have been set in state statute that we are to work to develop a climate plan for. And then biogenic greenhouse gas sources, which are those that extend from natural processes that are not the subject of our overall changing climate. Those, as the state commentators told you, there are changes to those systems happening as a result of increased anthropogenic activity, but the large increase in greenhouse gas emissions comes from anthropogenic sources since the industrial ages. The next topic I want to cover is a pretty important one. It's known as global warming potential. There's a nice graphic on the right that kind of explains what we're talking about. So greenhouse gases have a couple of different factors that play into what their impact on climate change is. How much is in the atmosphere? How long does it stay there? Some break down quickly, some last for hundreds of years. And then how strongly does it trap heat? And it's really the how long does it stay in the atmosphere and how strongly does it trap heat that define what we call a global warming potential. So the overall measure of that warming potency expressed as over a time period. Typically, and for the purposes of our greenhouse gas inventory, that is over a 100-year period. But other jurisdictions have begun to consider smaller timeframes when considering state or national level actions to take, because those global warming potentials change as you look at different timescales. So we express those the impact of different greenhouse gases as a comparison to carbon dioxide, so that we can all be talking the same language and we can use constant units and constant math. So for reference, the global warming potential of carbon dioxide is 1, because that's the baseline unit. For methane, which is the primary component of natural gas, it's 25. For some of the fluorinated gases, the HFCs, and other chemicals, you can get to up to 12 to 22,000 times the potency of carbon dioxide. So while the quantity of those gases isn't as high, there are significant potential warming trends, and where we've seen, it's in the HFCs and other industrial processes where we've seen significant growth globally over the last several years. Another thing I want to mention, and this is a key point, our greenhouse gas inventory tracks gross emissions. So it does not attempt to net out natural processes. It does not attempt to look at how, where we stack up overall. It is what our emissions are. There are a number of decisions that were made to develop the protocols that are based on international standards, but each jurisdiction does it slightly differently, and we'll go into some of those examples. You'll hear more about this in a few weeks, but the carbon sequestration is the active process of removing carbon dioxide from the atmosphere and storing it in another form, such as wood, where it cannot be released, and it's typically expressed as a negative value. Carbon storage is the total amount of carbon that we have stored in plant-based ecosystems, whether that be forests, wetlands, in our agricultural environment. And then the net flux in those systems is the rate of change in that stored carbon. And then finally, if we think about gross emissions as all of our anthropogenic greenhouse gas emissions, our net emissions become gross emissions minus that sequestration activity. How much is our natural systems pulling out of the air? There's some important considerations as Colin goes through the details of this inventory that I just want you to bear in mind. We do not have sensors around the state picking up every greenhouse gas emission that occurs. There's measurements, there's extrapolations from other data. We have developed protocols in order for us to estimate what the actual emissions are based on things we know, like the quantity of gasoline sold or other factors, based on what we know about how much carbon is in gasoline, for example. The greenhouse gas inventory, as I mentioned, is based on policy decisions about sort of what to count and what not to, and how to avoid double counting. So if I'll use an example. So we have landfill gas collection systems at our more recent landfills. Those landfill gas collection systems are either flared or used to produce electric power because the landfill gas is primarily methane and can be used to power a turbine. We do not count those avoided landfill gases that get collected as a mitigation measure, nor do we count the carbon dioxide from either the flaring or the burning of those fuels to create electricity, because we get into it sort of double counting. How do you actually factor in all those things? So it's an important point to sort of know that this is an estimate, and the way we count may affect some of the outcomes that you achieve in terms of which mitigation measures you select. It shouldn't necessarily affect the mitigation, which mitigation measures are going to be most important, but it may reflect how it shows up in the data. And then the same thing goes for wood heat. We do not count the CO2 from the burning of wood for heat or for energy, because we assume that it is less sequestration that's going on. This is also not a life cycle carbon analysis. We look at the emissions that are occurring either within the state in different sectors or consumption based, as we do in the electricity sector, since we're connected to a regional electricity grid. And then one note on sort of we have a lot of discussions about renewable energy and clean energy and emissions-free energy. There are lots of discussion points around that. Just to be aware that just because something is renewable doesn't necessarily mean that it is emissions-free, or and different jurisdictions take different perspectives on how to account for the carbon impact of various sources of energy. And so just want to help bear that in mind. We'll talk a little bit about our success in the electricity sector coming up later in the inventory, and where we go from here. And then just a quick note on inventories. You're going to hear inventory a lot in the next several meetings. The greenhouse gas inventory, which is what we'll be talking about now, is a specific subset of things. The two inventories that were directed as part of the GWSA work are programmatic inventories. What are we doing to mitigate the impacts of climate change, and what are we doing to make Vermont and Vermonters more resilient in the face of a changing climate? And with that, I will hand the mic over to Colin Smythe, who is the technical expert who puts together this work every year, and he will go through the details of where we stand as a state.
Great. Can everybody hear me okay? All right. Thanks, Peter. Well, thanks, Peter, for that introduction and for going over all those definitions. That's very helpful in jumping into this kind of overview of the inventory. So Peter touched on a lot of these points briefly already. I'm just going to run through them quickly again to reiterate some of the important ones. But let me just start off by, well, what is the inventory? So as Peter mentioned, it's kind of it's a quantification to try to capture all of the greenhouse gas emissions kind of associated with Vermont that are produced annually. And it's a report we publish annually that is required by our state statute. And as Peter also mentioned, the totals in there are the gross annual emissions, so they don't include the biogenic CO2 or any kind of the sequestration that he mentioned. And we try to make this as comprehensive as possible, so getting the emissions from every applicable sector that has greenhouse gases associated with it. And that's a pretty standard setup, and we maintain consistency with international inventory protocols and other states around the region, and kind of balance that with the available data sources. The gases that are covered, which Peter also touched on a few of those, but I'll go into a little bit more detail, are carbon dioxide, which is kind of the main contributor, methane, nitrous oxide, HFCs, which kind of include a whole suite of gases, PFCs, sulfur hexafluoride, which is the SF6 you see there, and nitrogen trifluoride. And those are the gases that are covered under the Montreal Protocol, which is kind of an international, intergovernmental kind of organization. I won't get into the details of that here, but anyway, it's kind of internationally agreed upon that those are kind of the main ones to focus on for inventories. And nitrogen trifluoride has been added at the end because that is kind of a more recent gas that's becoming a bigger concern. So we've added that in as well. So I mentioned that our methodologies are kind of consistent with these other international and national protocols and groups. It's also consistent with the Vermont Final Greenhouse Gas Inventory and Reference Case Projections report, which was done back in 2007. Some of you may be familiar with this. That was before my time, but that was a pretty comprehensive report done for Vermont. And so we rely on a lot of those methodologies still today and kind of adjust them where we need to. Peter, if you could do the next slide for me. So this is just kind of an overview of the main contributing sectors, and we'll get into the actual percentage contributions in the next slide. But you'll see these are all the sectors covered in the inventory. The fossil fuel industry, which is tiny on this slide, but most of the fossil fuels used in the state are actually encompassed in the other sectors in the inventory, which I'll get into later. The waste sector, industrial processes, electricity consumption, agriculture, residential, commercial, industrial fuel use, and the big one, which is transportation. And as I just mentioned, these sectors are also kind of the breakdown of what is included in each sector is also kind of adopted from that report I just referenced, the final Vermont Greenhouse Gas Inventory and Reference Case Projections. Next slide, please. So this is the breakdown, and I should backtrack a little bit here. So this is the breakdown for 2016. So the current greenhouse gas inventory for Vermont is from 1990 to 2016. And that is because a lot of these estimates rely on large federal data sets and tools put out by EPA. And it takes a long time for those large federal data sets to kind of get put together, modeled, however they are compiled, and then kind of quality checked and put out and published for everybody to use. So there's usually a several year lag time either in the data availability or potentially when EPA puts their tools out or when the tools incorporate that new data. So this is the latest inventory. The 1990 to 2017 inventory is in the process of being completed right now. It's not done yet, but it's on its way. But yeah, as you can see, kind of similar to the last slide, transportation is far and away the biggest contributor to our inventory, followed by the residential, commercial, industrial, fuel use sector, and then agriculture at 12.2%, and we kind of go down from there. But those are kind of the heavy hitters. Next slide, if you would, Peter. So we'll start off with the largest sector, and I'm going to kind of walk through all the sectors individually now, and kind of touch a little bit, at least, on the methodologies. And I'm not going to have enough time to go into the super in-depth methodologies, but if there are questions at the end, I'm happy to try to answer those. So as I mentioned, and you'll also see in the upper right-hand corner of these slides is just kind of a reminder of the percent contributions of all these sectors, so you can keep an idea in your mind as I'm talking as to how much these are contributing to our kind of overall profile. So kind of a preliminary note on this that I kind of mentioned is that we try to maintain these methodologies and keep them consistent through time so that our data is very comparable. Sometimes that's easier to do than others, and it really just depends on the available data, because it's sometimes hard to find accurate data sets that go back to 1990, which is obviously our baseline on which at least, well, 2 of the goals in the GWSA are based, and what our statute goals were based on previously as well. But anyway, we try to keep it as consistent as we can. So I just want to note that in the transportation sector, originally the transportation sector was done with an EPA state inventory tool, which is based on a lot of the same things as how we do it now, but it's just slightly different and not as sophisticated. In the recent years, since 2011, we've been using data from the National Emissions Inventory, and that is kind of a big report that EPA puts out every 3 years, triennial, and we supply them with a whole lot of county-specific data for on-road transportation, like age distributions and vehicle miles traveled and population data, things like that. And then EPA runs those through a sophisticated model called the MOVES model, that is kind of the state-of-the-art transportation model these days, and at least emissions model, transportation model. And so we feel that because we supply them with all that kind of high-level or detailed, local data, that those emissions are they're about as good as we're going to get. Using these other methodologies is not going to be as accurate as that. And so we decided several years ago that that was the best and most accurate way we were going to come up with emissions for this sector. And so I'll just add on to that for the years that are not NEI years, because it's only every 3 years, we try to just adjust those values based on vehicle miles traveled and fuel sales data. And that's just kind of using indicators to say that we feel that the emissions are going to go one way or another, because that's a lot of what the EPA MOVES model is based on. It's a lot more complicated than that, but that's kind of, the indicators we use for the interim years. So there's a lot more that goes into that, but that's where I'm going to stop the transportation sector for now. And if there are questions at the end, like I said, I'd be happy to try to answer them. So I'm going to move on to the second largest sector. Thank you, Peter. In the inventory, which is the residential, commercial, industrial, fuel use sector, and that sector is mainly heating buildings, but also heating water and cooking as well. For this sector, it's almost entirely based on an EPA state inventory tool, and it relies on one of the big federal data sets that I mentioned called the SEDS, or the State Energy Data System. And those are estimates put together by the Energy Information Administration, that kind of model based on a whole lot of different reporting done by states. They model the consumption of different fuels by kind of subsector, and it gets pretty granular. And so those are used to break it down into which of these sectors contribute the X emissions, and there are multiple calculations that kind of go into that tool as well. But that's kind of the baseline for it. So I will just note on here, as Peter mentioned, we don't include carbon dioxide from wood combustion in these totals because it's biogenic. And in this sector, the carbon dioxide from oil and propane is really the kind of main contributor here. And I guess tacking onto that biogenic piece, we do include methane and nitrous oxide from the wood combustion, just not the carbon dioxide. So I think that's where I'll leave the residential, commercial, industrial, or RCI sector, so I don't have to say it the long way every time, and move on to agriculture. So agriculture is the third largest piece of the puzzle here. It also relies mainly on default federal data sets and an EPA tool. It's based mainly on animal populations, and that's because the sector is comprised mostly of methane, but there's also some nitrous oxide in there from fertilizer use, and yeah, some kind of soils data incorporated in there as well. So the main piece of this sector is enteric fermentation, or methane kind of from the digestive processes of ruminant animals. But as you can see, I've kind of broken it down in a little pie chart on the right. There's also manure management is a portion for sure, and the agricultural soils. So there are multiple contributing factors in there, but that's mostly default data from the USDA. I will just note also on here that that anaerobic digesters are kind of a piece that fits into the scheme of this, and we do account for those in that we take kind of the contributions from the animals that would contribute to the manure management portion of the inventory, and kind of subtract those out. So the methane from that particular piece is not included in here. I think that's about it for agriculture. So moving on to the next one, which is a little more variable. The electricity sector is, it's not a gigantic contributor in the inventory, certainly not anymore, but it's important in that a lot of the mitigation strategies that Peter had touched on before, not all, but a lot of the big ones rely on electrification. And so it's a key component, even if it's not currently responsible for a large chunk of the emissions. So I'll go into just a little bit of and fairly high level of how we do the calculations for this sector, but just want to touch on first that as Peter mentioned in the beginning, we do this based on electricity consumption. We don't generate that much electricity in Vermont, and so we have to import a lot of it. And we felt that it was kind of a more fair representation to include the emissions associated with all the electricity that Vermonters use, rather than just what we generate in state. And a lot of other states do that as well, which is good, because if different states use different methodologies, you could have a double counting issue like Peter mentioned. but we do feel that that's kind of a more fair representation. So how we do it with this sector is we kind of have the total kilowatt hours from the public service department that are purchased by each utility, and the generation type that produce those kilowatt hours, and then we just apply an emissions factor to those different generation types that are based on data from the Independent Systems Operator, or the ISO. In this case, ISO New England. I will also just note that the majority, the vast majority, I think 98 to 100% of emissions from the electricity sector, at least certainly in the last couple of years, is based on the emissions from what's called the residual mix, which is kind of a leftover pool of electricity that's doesn't have any environmental attributes associated with it anymore, at least. And so that is kind of the factor. How much of that electricity is purchased by these utilities is kind of the driving factor in the emissions from the sector. But we'll also note that with the passage of the renewable energy standard, the kind of requirements for the amount of renewable energy, which generally in the electricity sector means low carbon, at least how we define it. And so that number is not likely to go up drastically. I think it could move around a little bit, certainly, but I think that should keep it relatively low going into the future. And just one other note is that our electricity is pretty carbon free, mainly because of our large purchases of hydroelectricity. And in the last couple of years, some purchases of nuclear energy, which is also considered low carbon. So that was a little bit more in depth than I meant to go, I guess. But we'll move on from there in the interest of time to the next sector, which is the industrial processes sector. So this sector, Vermont doesn't have a whole lot of these processes occurring in the state that are at least kind of captured within the framework of this sector. The two main ones are called ozone depleting substitutes, or ODS substitutes, and semiconductor manufacturing. So the ODS substitutes are, they're really mainly hydrofluorocarbons, and they're used for things like refrigeration, aerosols, insulation, that sort of thing. And their use is growing pretty rapidly, but I won't get into this too much either, but Vermont has recently passed Act 65, which is going to work to kind of phase these out. The other well, let me go back to the methodology. For that, because there is not an abundance of data that we have for that sector, we rely currently anyway on a tool that California has developed to estimate emissions for that sector that they kind of produced for the U.S. Climate Alliance states. And so we rely on those estimates right now, but are potentially going to look to refine those a little bit going forward. Moving on, the other piece of this sector is the semiconductor manufacturing emissions associated with that. And those emissions, at least for Vermont, are reported directly to EPA. And so we are able to kind of just pull that data and keep pretty good track of those. That's relatively straightforward. But I'll just also note that most of the emissions from this sector are, I think all of them actually are anthropogenic. So they're all human caused, and they're all kind of human made F gases, they call them. So they're the HFCs, the PFCs, sulfur hexafluoride, and nitrogen trifluoride. And as Peter mentioned in the beginning, the problem with this sector especially, is that a lot of these gases have very high global warming potentials. Sulfur hexafluoride has the 22,800 global warming potential. And while I'm talking about global warming potentials, I will also just note that we use the GWPs from what's called the AR4 report. which is, there is now an AR5 report out, which is kind of the newer version that has some updated values, but in case it comes up, the current guidance for inventory preparation is to use the AR4 ones. And so that's what we do at this point until that guidance is updated. Anyway, thank you, Peter. If you could move on, that'd be great. So the waste sector is, we're kind of getting down there in terms of percent contribution. It's actually the second smallest sector in the inventory, but it's comprised of both wastewater and solid waste. The wastewater totals stay pretty constant, and they're also based on an EPA inventory tool. But the solid waste sector is a little bit more involved in that Peter described a little bit of the methodology for that in his kind of preamble. And so we essentially have the reported landfill gas totals where almost all of these emissions are coming from in the waste sector. And they are reported through the Air Quality and Climate Division's point source registration program. And so we're able to take that data, kind of the amount of landfill gas that comes through those engines, and take some assumptions on the amount of fugitive methane that gets out of those systems, and come out with some numbers that we have pretty good confidence in. They're fairly detailed rather than being kind of the default data from a large federal data set. So that's definitely kind of a nice piece for that sector. And we'll just kind of give a nod to the Universal Recycling and Composting Law, which is also helping to keep the organics out of the landfills, and which obviously generate methane, a fair amount of methane of their own. And so that's also helping to kind of drive this down, as well as just these landfills aging over time and the landfill gas totals declining as they go. So moving on to the last sector, thank you, Peter, the fossil fuel industry. And fossil fuel industry, it sounds big, as I mentioned, but as you also probably heard me talking about, most of the fossil fuel in the state is going to be covered in the residential, commercial, industrial fuel use and the transportation sector. So this sector really just gets at this point, all it covers is the transmission and distribution of natural gas in Vermont. And so we take data from pipeline data and number of services data, and just apply leakage rates from the Code of Federal Regulations. And as you see, it's slowly going up because more services and additional lines are being added, but it's still a very, very small part of the overall piece at less than 0.1%. So that's pretty much it for kind of all the individual sectors in the inventory. I'm going to touch on a couple more of the kind of sequestration and biogenic carbon dioxide here. Oh, and sorry, I forgot this one. This is the column preliminary estimates. So we understand, and I mentioned that the current inventory is only through 2016, and we understand that people want as up-to-date information as we can possibly get on this, which absolutely makes sense. And so in the last inventory, we tried to project or estimate as best as I could out for the next 2 years, kind of as recent data as I could get, knowing that there were certain sectors where that wasn't entirely available. And so these are estimates that kind of comprise the normal methodologies, as well as data being carried forward, or kind of different methodologies for extrapolating on this. And there is additional information in the actual report on these, if you would care to look at that, but I'm not going to go into the details of it in here, but those estimates are available, and yeah, the 2017 is much better than the 2018, but we're putting it together as best we can.
Thanks, Colin. Colin, before you go on, let me just anchor here quickly. I think it's you showed the general noise in the electricity sector, but there's a trend that we're tracking that I think is really interesting for us to look at as we think about strategic electrification. You've got the black numbers in 2017 and 2018 are the ones that we have confidence in. And you'll see that there's a significant drop in the electricity sector based on demand in 2017 and 2018 to the point where it drops down from 8% or so of our overall emissions down to about 2%. So hoping that trend is continuing. Obviously, that's been a policy focus of the state of Vermont and the region. And so hoping that continues to play. But I just wanted to sort of highlight that for folks as one area where we're seeing improvement and hoping that remains a consistent trend and isn't just noise.
Yeah, great. Thanks, Peter. That's a great point. Anything else you want to add, or you all set? All right. So let me get through these last few slides here and hopefully have time for a few questions. So just want to touch a little bit on the forestry and land use sector, or what is called the land use change and forestry sector in the inventory world. It's obviously an important piece of the whole carbon cycle. We don't have great data on the land use sector, at least that can be kind of quantified annually at this point. And that makes kind of coming up with totals that we have confidence in a little bit tricky. But that's a common problem for lots of different states in the region. Pretty much everybody has this issue. And some people are working on kind of different data sets to try to come up with solutions to this, but to my knowledge, there aren't a whole lot of great ones at this particular moment. What we do have is we have a little bit better data on the forest carbon sequestration side of things. We have estimates on sequestration rates that are from the Forest Service, from the Forest Inventory and Analysis data set. And those are extracted right from the EPA's National Inventory Report data for us and other states as well. And you can see kind of what those estimates are based on the slide, but I will just note that that the sequestration rate has been gradually declining, as you can see on the graph over time. So so not as much sequestration has been occurring. Which is just kind of an interesting trend to note. But I will also mention again, as Peter did, that the emissions in this report, we track sequestration from forests, but it's not subtracted out of our gross totals. Next slide, please, Peter. And so I'm going to also touch on the biogenic carbon dioxide piece of this. So the biogenic carbon dioxide was, it's also not included in the gross totals. These are emissions where it gets a little tricky that would also be kind of double counted in the land use sector. But we don't currently really quantify the land use sector except for forestry. So there's kind of an interesting dynamic and all that, but I just wanted to touch on a little bit of kind of these biogenic carbon dioxide emissions. And the idea, or part of the idea, is that, as kind of why these are considered differently, is that these are also kind of carbon that's in shorter term storage. So it's kind of trees versus kind of fossil fuels that have been in the ground, kind of in the geological carbon cycle. So that's an interesting distinction, and is important to a point, but it also kind of depends on the type of biogenic carbon we're talking about and the timescales we're talking about. So it's assumed that the kind of combustion of this material or decomposition into carbon dioxide will be resequestered over time, and that's kind of where the whole carbon neutral argument comes from. But it depends a lot on kind of management practices and also, as I said, the time scales. So the kind of time scales, certainly for combustion, if you combust wood, it releases all the carbon in there as carbon dioxide at once. And then it takes time for that to be kind of resequestered, even with good management practices. And so that kind of differs, the estimates of the time scales required. But from what I've read, they are a little bit long, a lot of them at least, compared to our inventory goals. So not kind of weighing in one way or another, but just wanted to kind of flag that as a potential issue to be kind of thought about by the council. And if kind of the last point on this slide, sorry, Peter, is just that this graph shows the kind of what would happen if you included forest carbon sequestration, kind of the reductions, as well as the emissions of biogenic CO2. And the biogenic CO2 in this graph is only from the RCI and the electricity sector. But the black line is about where you get for a net amount of carbon annually if you accounted for those two factors. All right, thanks, Peter. So I'll very briefly touch on this one because there's kind of a lot here, but kind of another important piece of this that Professor Dupini-Giroux touched on was black carbon, at least briefly. And so black carbon, it's not a gas, but it does have kind of important climate forcing properties, if you will, direct and indirect. And for a direct impact, it's a component of particulate matter, and it's black, it's dark, and so it actually absorbs incoming solar radiation, so that kind of directly warms. And the other piece of that is that certainly in kind of Vermont, where we have snow on the ground, it also reduces the reflectivity or the albedo of snow, and so helps to melt the snow, which makes for darker surfaces, which also helps to absorb solar radiation. And so that's a more indirect warming, but still applicable. It's not quite as straightforward as that because it does have other implications for like cloud formation that aren't very well understood in terms of their warming or cooling properties. And that's still being studied as far as I know, but the other wrinkle being that it is also always emitted with organic carbon, which has climate cooling properties. So it's not incredibly straightforward, but the other important note for black carbon is that it has pretty significant health impacts as well. And so it is definitely known to be a warming agent and to have health impacts. And it's a very short-lived material from a couple of days to a couple of weeks. And it mainly comes from residential wood combustion in Vermont anyway, or diesel engines. And kind of the contributions of that aren't entirely clear. Diesel engines is much more clear, but residential wood is kind of the bigger source in Vermont. So anyway, I'm running out of time here, but I'm going on to the last slide. Is kind of just an overview of the historical estimates from 1990 to 2016, and you can see our 1990 baseline is the dashed black line at 8.65 million metric tons of carbon dioxide equivalent, and then you'll see the Global Warming Solutions Act goals, the 26% below 2005 levels by 2025, and then the 40% below 2030 levels. No, I'm sorry, below 1990 levels by 2030, and the 80% below 1990 levels by 2050. So emissions did go down between 2015 and 2016, but it's a little, yeah, I don't know. We've got a long way to go. And as my colleague Brian said to me a while ago, we have a long way to go and a short time to get there. So yeah, lots of work to do. that's about what I have for you. And yeah, I'd be happy to take any questions.
Thank you very much, Peter and Colin, for that in-depth review. We have Robert Leamer with his hand up. I just want to say Adam Knudsen and Richard Cowart's hands have been up since the last presentation, so just want to make sure that those are holdovers. So Robert, why don't you go ahead and ask your question?
Thank you very much. I'm enjoying this presentation very much. I've been sitting in on the commercial buildings energy labeling task force, which is remarkably granular, and a great deal of conversation as to the standards and how things flow from one area to another. And I just had a couple of questions. I noted that you mentioned the Montreal Protocol, which was in 1987, and that's when DOS was the primary operating system. It's obviously years before Windows 95, let alone modern operating systems. And the sensors and satellites and artificial intelligence and the other things that were available, that are available to us now, were not available then. And I understand that this is somewhat of an analog process. Coming up with emission sources, and decisions need to be made about anthropogenic and biogenic sources. There's some interesting crossovers in where things sort of change character, and the possibility of a great deal of leakage. For example, in the waste sector, when Burlington hauls 10,000 tons of sewage to Chattagouay, New York, 90 miles each way, is that in transportation or is that in waste? But I will have further comments in the audience participation program, but I don't want to hold up your meeting today at all. And I want to express my appreciation. Here's my question. My question is, given the relatively small resources that the state of Vermont can allocate to such a critical topic, are our methods consistent with, for example, the state of New York, which has devoted a great deal more resources in absolute terms to this topic?
So Robert, my apologies. I should have held you for the public comment period, and that was my oversight, but that's an excellent question. And I think as we look at the framework set in the statute, the Global Warming Solutions Act, for our conversations, that the efficacy of our programs is one of the items we have to look at, and the financing and the resources we have. And my full expectation is that within those conversations, which will most likely be in the subcommittees, that we'll be able to take a deep dive in. But we appreciate the comment and the question. I would like to move to Jared Duvall for his question or comment on the presentation, and Robert will get back to you in the public participation section. So my apologies for that oversight. Jared?
Thank you, Secretary Young. So I posted my question in the chat, but I'll just read it for purposes of the record. First, thank you, Colin, for your great work and the helpful presentation. But in the inventory that you were referencing in the presentation, the last published one that went through 2016, you also, for the first time, DEC and Agency of Natural Resources included projections out to 2021 and 2026. I was just wondering if you could say a bit more about what those numbers were based on and how they were arrived at, and also how much confidence you have in them and their predictive accuracy. Thank you. And I have a comment as well, but I'll leave that and just put it in the chat. Mainly, I want to ask Colin that question.
Fair enough. Thanks, Jared. Yeah, I will do my best to answer that. In terms of the confidence in the projections, they are just that. They are projections, and they're inherently difficult in that they are based on, honestly, a lot of modeling done by other people and other agencies. Specifically in our inventory, most of the kind of main sector projections were based on the annual energy outlook data provided by the Energy information administration. So I honestly would have to go back in to look at their very specific methodologies, but that's kind of, yeah, they rely on a lot of assumptions, and we kind of do the best we can to kind of make sure those assumptions make sense before putting it in there. But there are a lot of details that you just can't know. And also I will just note as well that that 2016 inventory was put out pre-COVID, obviously, and so there are certainly, that's another gigantic wrinkle in this whole thing moving forward with those projections specifically. So those projections, yeah, they're kind of the best we could do with the data we had available. But yeah, they are just that. They're kind of their projections based on a lot of factors.
Thank you. Adam Knudsen, your hand is up.
Well, Secretary, actually was addressed in the prior call. So for that hand raise, I don't. I guess since I have an opportunity, I'll take another one. The black carbon was new to me. In fact, we were brought an opportunity on black carbon manufacturing and a more clean way of doing that recently. So we've become more interested. Anything else that you can share about? Is this a recent trend with black carbon, or are there anything large scale changes that are occurring that are driving the black carbon aspect? And just so you know, the very specific part of black carbon that we're potentially getting in is changing its fuel source and production from natural gas to hydrogen. And hydrogen is a massive new technology, not new technology, but a way that's used as a fuel source. So if it's too deep technically, that's fine. We can come back to it. But interested in anything black carbon related on the trend side or use.
I can give that a shot. I don't have a ton of information on black carbon at my fingertips. I will tell you that we use black carbon estimates kind of right from the National Emissions Inventory and kind of break that down by sector. And so the 1990 to 2017 report will kind of have an update on that. But yeah, I don't know if I think it's always kind of been present. It may be that it is becoming more of a kind of visible, known issue. Honestly, I'm not sure about that. There may be others on this call even who know more about this than I do. But my understanding is that kind of the biggest, at least nationally, source would be diesel emissions. But with kind of a lot of the new emissions standards and emissions reductions technologies, that's really no longer the case, that's dropping very quickly as the vehicle fleet ages and these kind of new technologies are incorporated into the vehicles. So I think now that a lot of it is now coming from essentially wood burning. But I would have to go back to kind of say any more than that and look at some more of the technical details. So hopefully that at least gives you a little bit.
Yeah, that's helpful. Thank you. Appreciate that. I also think we might be dealing with a couple different definitions regarding the carbon piece. So thanks.
Sure, no problem.
Secretary, you're on mute.
Sorry. Thank you, Peter and Colin, again for your presentation. And it's now 10:35. We have a 15-minute break scheduled for 10:30, and I think we should take the break now, come back at 10:50 instead of 10:45. And then the next presentation will be the actual inventory of the existing programs that impact greenhouse gas emissions. So it will be a nice supplement to the presentation we just had on our profile. So please take 15 minutes, stretch your legs, stretch your back, hydrate, and we'll be back at 10:50. Thank you.
I'm going to stop the recording for the break.